Foot pedal controls, not just for musical instruments. What an odd change of topic, you might say. Why do a video on this right now? As it turns out, sometimes you go to record a video and realize that there's a few hours of work that you need to do before you can, and all of a sudden, oh, I don't have time, so I'm going to do this because I would do it anyway at some point. Who wants a cohesive narrative anyway? So the idea of a foot pedal is just you press on it with your foot, and it activates something. They're usually seen on pianos, where they're physical foot pedals. This one is from a digital piano, an electronic piano, a Yamaha it says on there, that I got somewhere between 1998 and 2002. They're used to change how the music instrument responds. And this is one I got from Sparkfun a few years ago. So obviously you can use them in their original purpose. You can do MIDI on a computer. But think about any time that you have your hands full and you wish you could tell the computer something, like if you're live streaming video gaming, for example, and you want to mute yourself briefly, like to cough. Imagine if you had a foot pedal you could press to mute your microphone. So you don't have to take your hands off the game, you don't take your eyes off the screen, you don't do anything. Just press on the pedal, and nobody can hear what you're yelling to your buddy in the next room, or your awful sneeze or whatever. Pretty much anything a button can do, you can imagine doing with a foot pedal. And there are analog and digital types. I have no idea what these are. We're going to open them and find out. So just like a trigger on a gamepad, you could have an analog signal, or it could just be a button, a momentary switch. Now they are designed for audio applications, so they have this big old plug. You can see how big that plug is. To plug this into a computer, now you might say there's all kinds of USB controls, that's true. But how many audio ports do you have on your computer that you're not using? Think about that. If you have installed your own sound card, you're not using the onboard audio, but it's still there. You can disable it in the BIOS usually, but it's not like you're going to run out of IRQs on a modern device. So you've probably got audio ports left over. So why not use that just like it's intended? This is an audio plug. The black insulator here, the tip is one conductor, and this is another. For your normal headphone ones that you'll see, they could be TRS, TRRS. It refers to tip, ring, and sleeve. So this would be the tip, just the tip. And then if there was more than one conductor, you would have just a ring between conductors, a little ring around it. So that would be the R, so T and R. And then S would be the rest of it, the sleeve. Now there is one complication. It's a simple enough matter to cut this connector off and solder on something else. And there may even be foot pedals you can buy that already have the right size jack. But some ports have what's called phantom power and some don't. Phantom power is basically, if you imagine this is not a powered device, this is not an active device. Think of a microphone. A microphone doesn't generally have fancy electronics. It could, but generally, like this is two conductor. This is a signal. Just like a switch or a button is a two conductor device. Two pin device, if you will. So depending on the port, you might need the computer to send power through this, and this would modify it. For example, if it's a resistor, this could be a variable resistor. And so the computer might apply a voltage, this would apply a resistance, and then the computer would read the current. That's one way it could work. So I'm going to have to do research on what my different devices use, but for now we're looking at the switches themselves to see how they work. So let's bust them open. Carefully, because I want them to still function. So I'll just use the surface of this breadboard for high contrast. So I'm going to start with the older one, the one from the Yamaha keyboard, piano keyboard that is. It says pedal 2 on the back, which tells me somewhere in the last decade I've lost a pedal perhaps, but let's not worry about that. So as I said, the connector is a TS. It just has the tip, then the insulator and the sleeve, so TS, and it's the large jack. I don't recall what it's called, but this large pin, which looks exactly like a regular headphone jack, this larger one is used for stereo systems, audio equipment. I don't particularly know why. It's probably some historic reason. Also, the greater surface area and diameter of the conductor might conduct better. Now, not when it's made out of basic metal like this, but if you had nice gold-plated silver or something like that, the greater diameter and surface area would make a difference, I'm sure. Something like this is not going to matter. So let's open her up. 4 screws. Now, one thing to keep in mind as you're opening up something like this, it's all well and good to say, I am just unscrewing the case. I'm not ripping anything apart, so surely it will go right back together. Be careful when you pull it open, because you don't know if things are connected to one side or the other. Especially when you're opening something like a phone, there can be ribbon cables all over the place, and just pulling open the thing, phones and laptops. You can yank on a ribbon cable and, oh, now you have to go to a repair shop and get a new connector soldered on. And also things can just be loose and fall out. So we just have the casing and we have the wire here. So the first thing to do is ascertain when I start pulling this up, does the wire come with? It does not. Also, it really wants to come up on its own. There's apparently some tension, and of course there would be, now that I think on it, because you have the casing screwing together, applying tension, so that the button snaps back up. Because otherwise the button would just stay down due to gravity. So when I loosen it up, it comes up. So the back of the casing has nothing on it, and we have, unsurprisingly, just a giant switch. So first you notice here there's a red and a white wire. We know there's only 2 wires, because there's 2 conductors on the plug. That's the minimum you need. The only way to send a signal with 1 wire is technically something like an optocoupler, which isn't even a wire. Or if you've got a common ground between 2 devices, which technically is 2 wires. So you're going to have 2 wires. So I see a red and a white. We flip up the switch, and we have a fairly standard design, so I can actually show you it this way. So you can see on here, this is similar to when I opened up the gamepad. There is a conductor here, and there's a pad on here, which when it's pressed, it goes in this little black spot, touches there, and will connect between the 2. So we can see that this one obviously is binary. There's no partial resistance here. All we have is it's a PCB with traces. It is that. But we've just got the 2 wires soldered on the bottom. 2 wires soldered on the bottom. 2 big old traces connected to those 2 spots. The writing on it is just model numbers. And that's interesting. This trace here, this down here, this copper looking line here, 2 copper spots, that says 400 ohms. But is that actually a conductor or not? I'm not sure if this is actually a 2-layer PCB. No, I can see through it. If I shine the light, which of course you can't see, but I hold it up to the light, there is no internal connection. So I'm thinking that is probably just an indicator to say that this is a 400 ohm resistor when it's connected, and an open switch when it's not. I could test this with my meter. Let's try that. If I can get my meter someplace you can see it. There we are, that'll do for now. So if it's 400 ohms, then let's put it on that setting, and it would be better if I could take this out. There we are. Carefully now, so I have this deductive process. Oh, I don't have any clamps nearby. Oh, I never have the clamps when I need them. So I'm going to first check to make sure that I get 0. Oh, that's volts. It would help to be on ohms instead of volts. So I short the connectors and we get 0 resistance. If I go across the 2 pads labeled 400 ohms, I'm going to have to get a better contact here, press down a little hard. It's oscillating, but I'm getting, 200, 300, 400. So factoring in oxidation and this being not the proper way to probe conductors, let's try pinpoint pressing, getting more like 100 there. So that's interesting. So if I measure across these 2 conductors, of course there's nothing. But what if I measure 2 spots on the same one? 5, 6 ohms there. So there might be resistance in this spot. So what I'll do instead is I'll go ahead and put this button on here, and I will measure, or try to, this is the jankiest possible thing, I'm going to try to measure on the connector itself. Now it's fine to press your fingers right on it, because your body has such a high resistance compared to this, it's going to not affect the mechanism much. So if I press the switch, I get about 24, 25 ohms of resistance. So obviously whatever this means with its 400 ohms is having no actual effect. So it might be that this is about 400 ohms of resistance if you connect it properly. So what you could do perhaps is solder some way to get that in the traces, or maybe during manufacturing they manufacture some with it connected there and some not. I actually have no idea. But that's interesting. Perhaps not useful, but interesting. This is why it's fun to take things apart, because you discover how they're put together, you discover little things like that. So now we will reassemble, because we now know that it is a simple switch. And of course it needs to go this way. And of course I'm wrong, because actually the button is in here. I had it backwards. So now we do this, and I just have to get this wire back in here. Fortunately, the cable kept its wiggles, so I don't have to wigglefy it myself. When you're smooshing it in, remember to be gentle and not stab your way through it. So I will just go ahead and put the screws back in. I need to stop being lazy and go ahead and magnetize my screw heads, or my screwdrivers rather. I even bought a little thing from the hardware store. There's only a couple bucks that you can magnetize any material that can carry a magnetic field. All right, a quick test to make sure we didn't break it. You always want to do that. So we'll measure resistance, short it, make sure it's working, and it is, and then test the connector. Press the button, switch closes, 22 ohms, good deal. So that is the one intended for use with an electric keyboard, an electric piano. I assume it just goes to the sustain function. So in a real piano, there's a foot pedal you can press, which basically that one is digital, binary. And there's just mechanics in the piano so that when you hit the note and you're holding the sustain, it slowly fades away instead of the note quickly going away. So you do that for drama, for reverb, just to make the notes persist a little bit. So let's look at the other one. This is the one I got from Sparkfun, which is a hobbyist electronics website. This one, the entire front of it actually pushes. The entire casing, in fact, pushes, whereas the other one was a button. So this one perhaps is easier to press in terms of just having your shoe on it, but it does take more force. So the first thing we do, of course, is look at the connector. This one also is only the tip and the sleeve, so no fanciness there, just the two. So a single signal. And also, we notice there are screws on the sides, and when I press this, it pivots on those screws. So we have to carefully undo these two screws, because it is essentially acting as a hinge. And yes, by carefully, I mean I'm holding on to it because it just tried to snap open on me. I'm having to apply quite a bit of force to keep it shut. So I'm going to undo this one, still applying force. And of course, now that it's trying to snap open, it's hard to get the last screw out. So I'm going to gently let it up so that I can analyze what's going on to make sure I can put it back together. And this thing is desperately trying to go to pieces. I can hear rattling, so I'm going to look, or try to, and see. Aha. There is a big old spring which is now fallen over and a button. Okay, so now I know it's safe to simply lift this lid. It's held on by friction, so now we have the front casing. And this spring was just loose in there. There is a small divot. There's actually a small divot in the middle right there. You can probably see it. So that the spring doesn't want to slide from side to side. There's quite a lot of tension, so it's not going anywhere. And if we look here, there's another divot right there. So the spring is just there, which is what pushes the thing back, and then it pivots on the screws. A nice mechanical solution. No additional parts, no additional fasteners, the same amount of metal, it just had to slam it with a little thing during manufacture. So on the back, we see there are two screws in the middle and one down here. So we look here, and we see that the screw on the bottom is connected to the wire. So that one is a cable management screw right there. That's just holding the wire in there to make sure it doesn't wiggle around. And then the other two screws are attached to this button. It's a button. There's not a PCB with a connection on it in traces. There is actually a button. And then they have soldered wires to the two contacts of this button. So this casing presses on the button. Essentially, this would be a transfer control. The other one, you press on the PCB and it makes a connection, and it's just a direct button like that. This one is an indirect button where you have a thing that presses a button. It reminds me of the old Macintoshes, the beige toaster days, where there was a debug signal you could send, but there was a button that was inside the case, and the only exposure was a very small hole. So you had a tool, a little plastic thing, that you could press and it would go inside the hole and press the button inside the computer. So it's similar to this. You might have a simple looking button here, and then on your front of your device, you might have a big old button that's just a plastic shaft that reaches in and presses this button. So there's no real reason to disassemble this further, partly because it's extra work, but partly because we can see everything. I can also see that the soldering is even crappier than my soldering, and I've been soldering for several days. The wire on this side is not so much in the solder as on it. And this one has just the tiniest drop of solder with a ton of bare copper. So clearly not a well-made device, but it works. Now the question is it a digital or analog signal? So I'm going to measure resistance, just like before. Test the probes. There we go. Now, so right now, of course, nothing's happening. So I'm going to press the button fully, and I'm getting about 4.7, 4.0 ohms. If I let go of the button at all, Okay, so if we are very careful, no. I'm being as gentle as I possibly can, and it seems like it's all or nothing. I can get it to go up to 100 some ohms for a moment, but that is more likely due to the delay in sampling of the meter than actually having a partial contact. So this is going to be another digital foot pedal. That's disappointing. I was hoping for an analog one, but there's no reason we couldn't, of course, use this casing if we wanted and put an analog one in there. I could take a potentiometer out of a gamepad or something and rig it up with this, because the gamepad already has the trigger, remember, where the plastic would press in and then that would turn into a rotation. So I could probably desolder one and stick it in there if I wanted. So we have two that are going to be just buttons, but that's all right. We can still do interesting things with that. So let me go ahead and put this one back together. And to no surprise, it's incredibly difficult to press now because I simply screwed it together. But these also serve as a hinge, so the screws have to be a little bit loose. You want to be just tight enough that they hold the thing together and don't unscrew over time, but loose enough that you can still press it. So now it's pressing fine. Just do it a few times, put your finger on the screw, make sure it's not turning, and we should be fine. And the final test, of course, is to make sure we didn't break it. This is me here. You always want to test to make sure you didn't break it. So I'll go ahead and touch both conductors, press the button, and we're good. A little bit of a loose contact. It could just be due to my fingers, and it is. Holding it tighter made it a nice stable contact. So it's perfectly fine. You're using your foot. This is a little harder with your hand, but your foot is going to put plenty of force on it. Not the most interesting teardown, but we still learn something. I absolutely encourage you to go to your local pawn shop or Goodwill store, dollar store, whatever. Grab some random electronics that are half broken. It doesn't even have to work. Go to your junkyard, go to a recycling center and say, hey, got some old electronics that you don't even want to deal with? I'll give you $5 and you give me a box of it. They'll be happy to give it to you and take it off their hands. Then you can rip it apart, see how it works, maybe even get some practice repairing. Take a cue from Louis Rossmann. Get old busted video game consoles, get old busted phones, get anything. You'll get practice and you'll get ideas. And while you do that, I'll be seeing you.